Today we're taking a look at section 13.1. This section is called Translations and Rotations. And what we're going to work with today to start with is a general term for both of those items and some more we'll discuss in the later sections called transformations. All right, so a transformation is a one-to-one correspondence from a plane to itself. Basically, a transformation takes an image and transforms it into another image. And by transforms, there are some very specific types of transformations that we're going to take a look at. A one-to-one correspondence will occur in these certain types that we're going to start with. So this is a relationship between two shapes where each feature in the first shape is paired with a corresponding feature in the second image. We call, I think this is later, but just so that I've said it and I'll reissue it when it shows up in our notes. The starting image, the starting picture, we call a pre-image, and the resulting picture is called the image. So pre-image from before, image is the after. Okay, pre and image, those are the two words we use. The specific type of transformation that we're going to talk about in most of what we're doing is called an isometry. An isometry is any motion that preserves length or distance. We say that two geometric figures are congruent if and only if they can be related by an isometry or a sequence of isometries. And the question is every transformation also an isometry? Okay, so a transformation is a manipulation of one shape into another shape. Does every manipulation of one shape into another shape have to preserve lengths and distances? No. In fact, you've seen some shapes that didn't do that when we did similar triangles, right? There was a one-to-one correspondence. This angle corresponded to this angle. This point here corresponded to that point there. All of them had these paired matchings, but their shapes were not congruent, right? One was potentially larger than the other one or smaller, depending on your perspective. So it's not true that we can always, or that we will always, have an isometry when we have a transformation. But the first ones we talk about are going to be isometries. Okay, so the two that we're going to deal with today are called translations and rotations, and these two will preserve distance. All right, so first one I mentioned was translations. A translation moves every point of an object a specified distance in a specified direction along a straight line. I should have used another word, specified, shouldn't I? I need one more of them in there. Generally speaking, it moves something left and down, right and up, left and up. Okay, you've got two sort of directional senses, and so it's moving things around. So it's a transformation if I take me here and I go like this. That's if I don't fall over. That's a transformation. Okay, and specifically it's a translation. Nothing changed except for the where I was located. So when you go up in an elevator, that would be a translation of you or of whatever's going up and down in the elevator. Okay, it's a movement of the object's location, all about location. Pre-image, I mentioned this before, I told you it was coming up. Pre-image is the original figure and the image is the resulting figure. And another phrase that means the same thing as translation is a slide. So translation is also called a slide because it's an action that mimics the motion of a child sliding. And you've got the picture and I do too. So the child is in the exact same position at the top of the slide as they are at the bottom of the slide. I mean, they may be smiling more or something, I don't know. But you know what I mean, right? Nothing changed except their position, their location of where they were. So sometimes you'll hear this translation thing called a slide. Okay, everybody good with that one? Yep. Okay. A little bit more about translations. In a translation, the image of all points are determined by a slide arrow. There's that word slide again. So that all parts move the same distance in the same direction. Sorry, I see a typo in what's on my screen. I don't know if it's on your paper or not. No distances, angles, sizes, or shapes are changed by a translation. So the image Yep, it's wrong on your paper too. The image, not the image, the image. The image created by a translation is always congruent to the pre-image. Because we don't change the size or anything of what's going on, it's congruent to where it started with. Different place and space, but it's congruent. All right. One way of representing or showing translations is with a dot grid. So you determine the direction and the distance of the slide arrow, and then move all points accordingly. And we're going to do an example. Here's my dot grid. You've got a dot grid. I need to draw a little bit of imagery onto here, so you can draw these in, because this is sort of the given question. It's just not on your paper. Okay? So in the top left-hand corner, I want you to draw an arrow that represents moving from those two dots. Okay, so connect those two dots on your paper. I'd like for you to call the bottom dot that I just created X. The top dot is going to be called X prime. And our arrow is pointed toward the X prime. So you've got an arrow pointed toward X prime. This is called the slide arrow. Okay? Basically what it's telling you is that the point X moves up 2 and right 1. That's what it's telling you. And the point X is every point on the original image. So let's actually draw what the original image is. And you guys can draw this one in as well. So here's my original image. Yeah, hang on, I messed one up. Too long. Okay, there's my original image. Kind of looks like a side view of a house maybe, or something like that. Okay. It's trapezoid, right? It's actually a trapezoid. And we're going to move this image in the direction that it indicated in the slide arrow. So every point is going to move up 2 and right 1 from where it was before. If it helps you, give your points names. Here's A, and here's B, and here's C, and here's D. If you don't want to do that, you don't have to. It's fine. But just for the sake of being able to talk about it all together, where will point A move? It needs to move up 2. Well, up 2 puts it like 1 above C. But it also needs to move over 1, right? So the point, let me change my color so I can talk about it, will move to right here. Now, you can also move the other point next to it, B. So B prime would be right here. If it moved up 2, it would be on top of D. To the right one, it would be on B. So these two are connected, if you will, like this. Now you can continue to move points individually. That's fine. Or you can continue to move the whole shape. For instance, I moved the bottom 2 units up, so I could build on that, right? On the left-hand side, I need to build it up 1. On the right-hand side, I need to build it up 2. So if I think about it from that perspective, it would look something like this, right? And then I can, if you will, connect the dots. So it should look congruent to the one that we started with, within a level of accuracy that's reasonable, of course. And we've just shifted everything. So if the picture you end with doesn't look like the picture you started with, you might not have shifted everything quite right. Okay? So these are dot grid translations. We're going to look at a coordinate grid translation next. You guys ready for that one? Okay. With coordinates, we can explain, so we can also explain translations using coordinates from the Cartesian plane. The translation shown from O, which is, excuse me, the origin, to O prime, which is the point -5, 2 on our picture, is applied to triangle ABC, which is the blue triangle. So what we want to notice is this image at the bottom, how it's moving things. So it looks like this image is not on your paper. Is that true? No, it is on your paper. I'm looking at the next one. I'm sorry. So this image down here at the bottom, how are the points moving? Can you describe them in words first? What are they doing?
To the right 5 and down.
The right 5 and down 2. Okay. So what is the right, left, or ordered pair value? Is it the X or the Y? X. X moves things right and left. So wherever X is, if it's moved 5 right, what are we doing to the X coordinates? We're adding 5. So we're going to write that as X plus 5. And then the Y coordinate moves things up and down, and this one moves it down 2. So our y value will be then minus 2. And in general, we can do that to any translation like this. We can look, how far left and right did it go? Do I add or subtract? And I manipulate the x value. How far up and down did I go? And I can manipulate the y value. Okay? So we're going to do an example because that's fun, right? Of course. Okay, it says draw the image of triangle ABC under the translation x minus 3, x plus 1. Then find the coordinates of the labeled point. Okay, so I know it says then, like there's an order to what you're doing here. If you want to do it backwards of the order they're suggesting, that's okay. So could you just find all of the ordered pairs, add and subtract the values, and then plot them? Sure. If that feels more comfortable to you, go with it. Take a look, though. I'm going to do it visually. Let's actually write down what this is doing. So what is the x minus 3 part doing? That moves it left 3. And what is the plus 1 doing? Moves it up 1. So I'm going to move each point itself. So let's start with B because it's the top value. If I move it left 2 and up 1, I think, oh, sorry, left 3 and up 1, I think this puts me here. What's that ordered pair, just so we all have the same thing? Okay, negative 2 first because that's the x value, and then 5 is the y value. I did point B. Yeah. So from point B, I moved it left 2, 3, and up 2, or up 1, sorry. Left 3, up 1. So I'm kind of drawing in my error. I'll erase it here in just a second. But I moved the point left 3, up 1. I called it A on the side there. Didn't mean that. I'll have to fix that too. How about we put the B prime? That's what we want. Okay, it's B. Kind of looks like a heart, actually. Okay, let's go with point A next. Point A. If I move it left 2, 3, 1, 2, 3, here we go, and then up 1, it puts me here. Agreed? So this is A prime. What is the ordered pair in that location, x, y ordered pair? Negative 4 and then 2. Is that a readable? That's like a dark, ugly mustard yellow. I'm trying to find a way that it's not going to be like unreadable on the white or unreadable on the darker color, the grayish background. I know I'm not being super successful. Let's try something different. How about blue? Okay, C. C needs to move left 3 and up 1. Where's that going to be? That's actually going to be at 0, 0. So here's C prime, and it's at 0, 0. And then what are we going to do with these 3 points? Connect them with a line between each pair, right? We're going to connect them with 3 lines, actually. With a straight edge, yes. Okay. And if we've done it right, it should look congruent to where we started. So if you get to this point and you're looking at it and you're going, yeah, that doesn't look quite right, time to go back and double check your work. It might just be that your drawing's not quite to scale. Perfectly possible, right? Or it might be that you actually moved something 4 instead of 3, or something like that. Okay, any questions on that one? Okay, the next type of isometry is a rotation. A rotation is we've actually talked about turn symmetries, right? This is the same idea, okay? A rotation is a motion of a plane determined by holding one point, the turn center, fixed, and rotating the plane by a certain amount, called the turn angle, in a certain direction, clockwise or counterclockwise. And I hope even as you write this down, you feel like, didn't we already do this? Because we really have, right? We didn't give it the name isometry before, but it is an isometry. The turn angle is the amount by which all points are rotated along a circle in a specific direction. Okay, so rotations in terms of tracing paper. You've got this picture in your notes as well. One way to do rotations is with tracing paper, and it works really pretty nicely. So what they're trying to show you the image of is that the brownish piece of paper or orangish piece of paper on my screen is the tracing paper, I guess, or whatever, and they've rotated it, holding it fixed at this point O that's in blue. So they've rotated that image, and as they've rotated what was already drawn, like drawn doubled, you know, it was drawn on the paper below and on the tracing paper, it ends up in the location of the blue triangle at the top. So can you kind of get the feel that that's what's happening? They've taken this image, and then they've held it fixed, and they've rotated the piece of orangish paper up. Okay, they could have rotated the clear one instead, but that's how the picture's drawn, is they've rotated the orange one. So the blue image is the final image, whereas the one that was drawn in black and dotted underneath at this point here was the pre-image. And they always write it so that the pre-image has the letters A, B, C, for example, and the image, the resulting figure, always has these prime notations. It's another way to keep track of where you're starting and where you're ending, is that they use those primes to indicate the final resting place, if you will, of the location of the object. Okay, so a little bit more about rotations.
So if you have like more than one rotation, they're like fine. It's like the final spot, but if you have like two, would it be like you do two dashes after that, or is it just?
Yeah, you would. So, and not even just a rotation, but two transformations at all. Yeah, so like let's say, and we won't do it in this lesson, but we will eventually do something where we've translated the object left two and, or right two and down one, and then we've rotated it after that. So the translated object would have the prime notation, and then the final one after the rotation would have double primes. So yes, we could do that. And I don't think, I'm pretty sure it's not the case, I'm pretty sure this is true, that you do any more than two transformations with any object ever in this particular book. So you don't need like triple primes or anything like that. Okay, a little bit more about rotations. In a rotation, the entire original image is, quote unquote, picked up and turned all at the same time. When that happens, no distances, angles, sizes, or shapes in the pre-image are changed. There's no change that's taking place. Because all of those things are preserved, this is an isometry. And everything has an identity isometry of 360 degrees. So that's not a real helpful description. If it takes 360 degrees to get it to turn all the way back down on itself, that's an identity. It didn't really do anything. Okay, now when we did rotations before, let me make one comment. All of our rotations in terms of symmetry rotated about the object's center. Think about it. We used the wheel, we used the pentagon, we used whatever, and it was always the point in the center that was our turn center, right? It doesn't have to be. So, as you see this first picture of the guy who's standing on his head and then he's standing on his feet, the point of rotation is not on the guy. We rotated the guy around this random point in between right here. Whoops, I'm using the wrong point at this point. Let me get a different color. Oh, please, come on. There we go. This point right here is what we're rotating about on this one, okay? So he turns he does like a cartwheel or something, right? Starts with his hands up or his head on the ground, and then he's doing a headstand, but then he has to cartwheel over to get out of it, right? Because now he's standing back up again. So this point around the rotation is not inside of the person itself, it's outside of him on this object. The same thing's true of the next one, what kind of appears to be like a flagpole, right? The point of rotation is actually right here in the middle, which is not on the flagpole. And over here, the semicircle, the point of rotation is not on the semicircle. So does it have to be that way? Well, no. The point of rotation could be on the object itself, but it doesn't have to be. All right? For some nice rotations, such as 90-degree rotation, a dot grid works really well for visualizing the rotation. And unfortunately, there are cases where flat out, it's just hard to visualize the rotation, okay? I used to joke, and I'm so much better at it now, especially since I have kids who are so much worse at it than I am, that my husband had to do the dishes because he could fit more in the dishwasher than I could. And he really could. I'm not joking. He really could. He could visualize how to make better use of the space. It's the reason every time we've moved, he's loaded the moving truck in so much more of an efficient way than I have. He can visualize how to use space really well. And it's something that does not come as naturally to me, but my kids are way worse at it. So now I don't get the excuse because I'm constantly reorganizing the dishwasher to fit more in. So we're going to try our best to do these visualizations of rotating images, but I will promise you in advance, I'm not very good at this, so I'm probably going to make some mistakes. So just have a little grace with me on this because this is not a forte of mine because I don't visualize very well, okay? All right, so here's an example of one. it tells us to find the image of the following quadrilateral in a 90-degree counterclockwise rotation about O. All right, so one thing to realize about this question is you are welcome to get a sheet of paper and draw it on that sheet of paper and cut it out and turn it and put it back down. If that helps you, fantastic. Grab some scissors, okay? You can do that. We're going to try to do it without that together and see how big of a mess we can make. Okay, so let's give it a go. We have this object. It says 90-degree, let me move this closer to me. A 90-degree rotation is counterclockwise. So counterclockwise means we're going to take this object and how are we going to move it? This way, right? This is counterclockwise. So it's still going to look like this object when it's done, but it's going to be somehow up and down instead of laying on its side. Agree? Okay, we're going to take this object first. And if I rotate it 90 degrees, where will it land? It'll land vertically. Okay, so that's my first object. And again, you can use letters to label things if that's helpful. Did you say something, Alyssa? Let's label them. Okay, so I already have O labeled, agreed? So what else letters do you want to use? A for Alyssa, right? Absolutely. And H is Hannah because you're next to, I can't use your name, Asia. I already got an A. I'm sorry. J. J, you're in the back corner, so we'll use your J. Okay, so you guys got my letters. So OH is going to flip from being a horizontal segment to being a vertical segment from O up. So the O point actually doesn't move, correct? Okay, so let me make that a little bit darker. How about that one? There we go. So this will be O prime. O and O prime will be the same, and this up here will be H prime. Okay? How about this section OA? Where is it going to rotate to? OH. It'll rotate to being on top of OH. So the H location, okay, so the segment OA will now be right here. Sorry, it's not perfectly on there, but the points start to get messed up if I try. And this will be actually A prime now, right? So this H location is the same as A prime. Okay. Those two I'm pretty good at rotating usually because they touched O to start with. It's the after effects of that I get a little bit more difficult. If you think from A to J, and A is now here, will this segment, where will this segment that I'm trying to draw go? It will be vertically up to. So our reference point, notice, was not really the reference letter or the point O. It was the reference point A because we already had it on the diagram. So the point that's in the air, really high now if you will, is actually J prime. And I can connect these two over here to finish out the shape. So if you imagine rotating this, will it land there? Yes, it will. Okay? Now, word of caution. It's harder when the rotation is not on the object. So let me try with you. This is off the cuff trying with you, so this might not work well. We're going to try moving the center of rotation and see what happens, okay? I shouldn't do this. This is a bad idea. Okay, we still had our same letters. This was H and A and J. Sure, just draw yourself another picture. You're probably going to have to scratch it out because we're going to mess it up anyway. Just warning you right now.
Positive self-talk.
Positive self-talk. I should be, yes. Let's try the C, and we'll call C for like turn center C. Okay. This is such a bad idea. Okay. All right, notice the point from C to A is down 2 and right 1. Correct? And we're trying to rotate this by 90 degrees. So this 90-degree angle right here will get rotated up to here. The whole object's, the whole screen's getting rotated. So instead of going down 2 and right 1, we're going to go right 2 and up 1. So this point up here is actually going to be A prime. And in some sense, if you kind of draw them in, I'll draw it in dotted to try to make the argument a little bit more convincing, because I'm not convinced. I don't know about you. But we rotated this like this, and do you see the 90-degree angle here? It really is a 90-degree angle there. It's harder to do, but it's because it went down 2 and right 1. Do you see that triangle that you could form right here? And if you go right 2 and up 1, you get that same triangle. So this triangle gets rotated up here. Okay, from point A, how do I normally, in the original diagram, get to J?
What is the C?
Over 2.
That's the point I'm turning it around.
Okay.
This is my new orientation or whatever. What did I do, Leah?
I would say that's like the O from the previous one.
Yes, it's the O from the previous
Does
example.
that have like a name and she's turn center?
It's the turn center. Yeah. So in order to get from A to J, it's 2 lengths long, right? And it goes 2 to the right. But what will it do when I rotate something that's 2 horizontally? It will be 2, not left, up and down, 2 vertically. So my image, I don't have a screen that actually goes far enough up, but it's up here. Because I told you this is a bad idea. All right, here's J prime. So this image that I just got right now, it matches this right here.
How do we know where to put A prime?
Because that's what I went through before, and I drew dotted lines, and I already erased them, so now I got to get them back.
Okay, sorry.
Okay, hang on, let me put that back in. All right, what did I do? Redo, 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 redo. I want that there. So there's 2 ways that I described it, Hannah.
Okay.
One way is that if you notice from C down to A, we go down 2 and right 1.
Okay.
You could actually almost imagine putting a triangle right there. And if you rotate that whole triangle to here,
Okay.
you get this piece, which is 2 to the right and up 1.
Okay.
If you imagine drawing in the triangle, it's a little bit more helpful. You think about rotating the triangle here. Can you see the triangle being rotated? And you also notice, if you're drawing them the right way, that this and this, when we connect them, well, I mean, you got to do it in a convincing way, and I just totally didn't. But hang on, I didn't connect it to the right place. That's why it wasn't convincing. Is that there's a 90-degree angle here. Do you see this, Hannah?
Yeah.
It's 90-degree angle here.
Yeah.
Okay. All right. Once we've rotated A, oh, I didn't draw that one right. That's probably part of my problem at this point. It's way easier if it's on the object. Okay, here's AJ. A prime, J prime. All right, so notice the point A. Actually, you know what? Let's just do O. C to O. What do you see from C to O? It's what? Down 1, right 1. So, and it creates this little right triangle. So instead of going down 1 and right 1, what should we go? Right 1 and up 1. So O should actually be right here, O prime, with the connector right there. And again, if we connect them together, CO and CO prime, the lengths are the same because it's a diagonal of these little squares, and there's a 90-degree angle formed right here. Do you see it? Right here, this 90-degree angle. Like right in here. Okay, so that's the 90-degree rotation. This is all counterclockwise. We could go clockwise as well. From O to H, we go 1 to the right. And if I rotate that, that becomes 1 up. So this one will go right here. Right there. So there is H prime. And we connect the last 2 right there. Same object, and it's been rotated. It didn't end up a disaster, so that's good. Very good news.